Ever wondered how AI can be both powerful and private? How can we train massive models on sensitive data without compromising user privacy? The answer lies in a revolutionary approach to machine learning: federated learning. Imagine a world where your data never leaves your device, yet you contribute to building incredibly accurate AI models. That's the promise of federated learning, a paradigm shift in how we train and utilize artificial intelligence. Join me as we dive deep into the world of federated learning, exploring its inner workings, its vast potential, and the impact it's poised to have on our technological future. So, what exactly is federated learning? Imagine a network of devices, each with its own local data set. Instead of sending all that data to a central server for training, what if the training happened locally on each device? That's the core idea behind federated learning. Each device trains a local copy of the AI model using its own data. These locally trained models are then sent to a central server, not the data itself. The server then combines these updates into a new, improved global model, which is sent back to the devices. This cycle repeats, with the model getting smarter with each iteration, all while the raw data remains safely on the individual devices. It's like a giant collaborative learning effort, but without anyone sharing their personal information. One of the most remarkable aspects of federated learning is its emphasis on privacy preservation. In traditional machine learning, data is often collected and stored centrally, making it vulnerable to breaches and misuse. Federated learning flips the script by keeping the data where it belongs, with the user. Think of it like this. Instead of sending your personal photos to a company to train a facial recognition model, your phone would train a local model on your photos. Only the model's learnings, not your actual photos, would be sent to the central server. This ensures that your private data remains private, addressing a crucial concern in our increasingly data-driven world. Federated learning thrives on decentralization. Instead of relying on a single, powerful server to handle all the training, it distributes the workload across countless devices. This has profound implications, especially in scenarios where data is inherently distributed. Imagine trying to train a language model on how people use emojis. Collecting all that data in one place would be a logistical nightmare. But with federated learning, each phone could train on its users' texting patterns, collectively contributing to a global model that captures the nuances of emoji usage across different demographics and languages. Federated learning isn't just about privacy, it's also incredibly efficient. Traditional machine learning involves transferring massive data sets across networks, consuming both bandwidth and computational resources. Federated learning sidesteps this bottleneck by processing data locally. Now think about training a model on smartphone sensor data. Instead of uploading gigabytes of data from millions of phones, federated learning allows each phone to process its own sensor data, only sharing small model updates. This significantly reduces the amount of data that needs to be transmitted, making the training process faster and more bandwidth efficient. As the number of connected devices explodes, so too does the potential of federated learning. This approach is uniquely suited to handle the massive scale of data generated by billions of smartphones, wearables, and IoT devices. Traditional machine learning approaches often struggle to keep up with this data deluge. But federated learning can tap into the collective processing power of these devices, enabling the training of incredibly complex models that would be impossible to create otherwise. It's like harnessing the power of a global supercomputer, one device at a time. Let's peek under the hood and see how federated learning works in practice. The journey begins with model initialization. A basic version of the model, the global model, is created and sent out to the participating devices. This initial model acts like a blank slate, ready to be molded by the data it encounters on each device. It's important to note that this global model doesn't contain any pre-existing knowledge or biases. Its learning journey truly begins when it reaches the individual devices. With the global model in hand, each device embarks on its own personalized training regimen. Using its local dataset, the device tweaks and refines the model, adapting it to the unique patterns present in its data. Imagine, for instance, a smartphone keyboard app using federated learning. Your phone would train the model on your typing style, learning your commonly used words, your slang, and even your typos. This personalized training is what makes federated learning so powerful. It allows the model to become an expert on the specific data it encounters on each device. Once the devices have completed their local training, it's time to share what they've learned. But remember, we're not sharing data, just the insights the model has gained. Each device sends its updated model back to the central server. Here, a crucial step takes place. Aggregation. The server acts like a master chef, carefully combining the learnings from all the devices into a new and improved global model. This aggregation process is the heart of federated learning, where the collective intelligence of all the devices is distilled into a single, more powerful model. Federated learning is not a one-and-done process. It thrives on iteration. The improved global model is sent back to the devices, and the cycle begins anew. Each iteration builds upon the previous one, with the model becoming progressively more accurate and robust. This iterative nature is crucial for adapting to changing data patterns. As new data is generated on devices, the model can continuously learn and evolve, ensuring its predictions remain relevant and accurate over time. It's a continuous feedback loop driving the model towards greater intelligence. Imagine a world where hospitals could collaborate on training life-saving AI models without sharing sensitive patient data. That's the potential of federated learning in healthcare. Hospitals often hold vast amounts of patient data, but privacy concerns restrict data sharing. Federated learning offers a solution. Hospitals can collaboratively train models on their combined datasets without ever exchanging raw patient information. This could lead to the development of more accurate diagnostic tools, personalized treatment plans, and even the discovery of new drug targets, all while upholding patient privacy. In the financial sector, data is king, but so is security. Federated learning provides a way for banks to leverage customer data for enhanced services while maintaining strict privacy standards. Imagine training a fraud detection model. Instead of pooling all transaction data centrally, each bank could train a local model on its own customer data. These local models could then contribute to a global model, creating a more robust and accurate fraud detection system without compromising the privacy of individual customer transactions. Our mobile devices are treasure troves of personal data. Federated learning can tap into this data to deliver highly personalized experiences without compromising user privacy. Think about keyboard apps that predict your next word. With federated learning, these apps can learn your unique typing style and vocabulary without ever sending your personal messages to a central server. This ensures that your private conversations remain private, while still benefiting from the power of personalized AI. The Internet of Things, or IoT, is connecting our world in unprecedented ways. From smart homes to connected cars, countless devices are generating data every second. Federated learning can harness this data to make these devices even smarter. Imagine smart thermostats using federated learning to optimize energy consumption. Each thermostat could learn the unique heating and cooling patterns of a household, contributing to a global model that improves energy efficiency across millions of homes, all while keeping individual household data private. While federated learning offers numerous benefits, it's not without its challenges. One of the key considerations is communication overhead. The frequent exchange of model updates between devices and the central server can put a strain on bandwidth, especially in resource-constrained environments. Researchers are actively exploring techniques to minimize this communication burden. These include compressing model updates, reducing the frequency of updates, and even selecting only a subset of devices to participate in each round of training. Finding the right balance between accuracy and communication efficiency is crucial for the widespread adoption of federated learning. Another challenge in federated learning arises from the heterogeneous nature of data. The data on each device can vary significantly in size, quality, and distribution. This variability can introduce biases and inconsistencies into the training process, potentially impacting the accuracy of the global model. Addressing this challenge involves developing robust aggregation techniques that can effectively combine model updates from diverse data sources. Researchers are exploring methods like weighted averaging, where updates from devices with higher quality data are given more weight, ensuring that the global model benefits from the most reliable data sources. While federated learning is inherently designed with privacy in mind, ensuring the security and privacy of the entire system requires constant vigilance. Even though raw data isn't directly shared, malicious actors could potentially exploit vulnerabilities to infer sensitive information from model updates or compromise the integrity of the training process. Researchers are actively developing techniques to enhance the security and privacy of federated learning. These include differential privacy, which adds noise to model updates to obscure individual data contributions, and secure aggregation protocols that prevent the server from learning anything about individual device data during the aggregation process. As we've seen, federated learning has the potential to revolutionize the way we develop and deploy AI. By keeping data private, distributing the training process, and enabling collaboration on an unprecedented scale, federated learning unlocks a future where AI is both powerful and responsible. Imagine a world where medical breakthroughs are accelerated, financial services are more secure, and our everyday devices are tailored to our needs, all while respecting our privacy. That's the promise of federated learning, a technology that's poised to shape the future of AI and, by extension, our world. If you're as fascinated by the potential of federated learning as I am, make sure to hit that subscribe button and ring the notification bell so you don't miss out on our future explorations into the cutting-edge world of technology.